In the vast, silent theater of space, black holes have long been cast as villains, cosmic monsters that consume all light, all matter, and all hope of escape. To fall into one is to vanish forever, erased from the universe, never to return. At least, that's what we once believed. Then came a revolutionary idea, an idea so bold, it turned physics on its head. What if black holes weren't entirely black? What if, despite their immense gravity, they could slowly bleed energy, emit radiation, and, given enough time, even evaporate? This is the story of Hawking radiation, a mysterious, nearly imperceptible glow that emerges from the very edge of a black hole. First proposed by the legendary physicist Stephen Hawking, this phenomenon connects the deepest laws of gravity, quantum mechanics, and thermodynamics, and may be the key to solving one of the greatest puzzles in science. Black holes are among the most extreme objects in the universe. Born from the collapse of massive stars, they contain so much mass in such a small space that their gravitational pull becomes irresistible, even to light. At their boundary, known as the event horizon, the escape velocity exceeds the speed of light. Beyond it, nothing can return. For decades, black holes were thought to be perfect cosmic prisons, completely black, with no way to observe what lies inside. According to Einstein's general theory of relativity, once something crosses the event horizon, it's lost forever. Information, matter, and energy vanish into an unreachable singularity at the center. But this view left physicists with a troubling paradox. If black holes only absorb and never release, what happens to the information that falls in? Can energy just disappear? Or is something missing from the picture? That something would come not from general relativity, but from quantum theory. At the smallest scales, the universe is governed not by gravity, but by quantum mechanics, a realm where particles pop in and out of existence. Uncertainty rules, and nothing is truly still. Even the vacuum of space, what we think of as empty, is seething with quantum activity. According to quantum field theory, pairs of virtual particles are constantly forming and annihilating everywhere, even at the edge of a black hole. Normally, these pairs cancel each other out almost instantly. But what happens if this process unfolds right at the event horizon? Stephen Hawking asked this question in the early 1970s, and his answer would change everything. He proposed that if a virtual particle pair forms near the event horizon, it's possible for one particle to fall into the black hole while the other escapes into space. The escaping particle becomes real radiation, while the other, having fallen in, removes a tiny amount of the black hole's mass. This process leads to the astonishing conclusion: black holes can emit radiation. Over immense spans of time, this radiation carries away mass and energy, causing the black hole to slowly shrink. The radiation predicted by Hawking is not like the brilliant emissions of stars or galaxies. It's cold, faint, and nearly impossible to detect. The smaller the black hole, the hotter and more intense the radiation. For stellar mass black holes, the temperature of Hawking radiation is colder than the background of the universe itself, rendering it invisible to current instruments. But in theory, the implications are profound. If Hawking radiation is real, it means black holes are not eternal. They radiate energy, lose mass, and eventually, billions or trillions of years from now, they will evaporate completely in a final, explosive burst. This evaporation poses deep and unsettling questions. What happens to the information that fell in? Is it lost forever, violating the laws of quantum mechanics? Or is it somehow encoded in the radiation, scrambled, and spread across the cosmos? These questions form the heart of the infamous black hole information paradox, a conflict between the two most successful theories in physics. Quantum mechanics insists that information cannot be destroyed. Every particle, every interaction, must be reversible in principle. But if a black hole evaporates and disappears, what happens to all the information it once held? Stephen Hawking himself once believed that information was lost. But this violated quantum theory and led to decades of debate, division, and deep investigation into the nature of space, time, and reality itself. Newer ideas suggest that information may be preserved at the event horizon, encoded in subtle quantum states that somehow escape as Hawking radiation. Others point to theories of holography, where all the information inside a black hole is projected onto its surface, much like a 3D image stored on a 2D film. In recent years, breakthroughs in quantum gravity and string theory have given hope that the paradox can be resolved. But the final answer remains elusive, and Hawking radiation remains unproven in practice, despite its deep theoretical foundation. The direct detection of Hawking radiation is one of the greatest challenges in modern astrophysics. Because the signal is so faint, especially for large black holes, it is easily drowned out by the cosmic microwave background, the ambient radiation left over from the Big Bang. Some scientists hope that primordial black holes, tiny black holes formed in the early universe, might be small enough to emit detectable radiation today. Others are building analog systems in laboratories, using fluids, sound waves, or lasers to simulate event horizons and observe similar radiation-like effects. These experiments cannot recreate gravity itself, but they might shed light on the quantum processes that give rise to Hawking radiation. In the meantime, we continue to search the skies, looking for the final flashes of evaporating black holes, brief gamma-ray bursts that could reveal the phenomenon in action. If Hawking radiation is real, and most physicists believe it is, it means black holes are not the ultimate end. They are thermodynamic objects with temperature, entropy, and a finite lifetime. Over unimaginable time scales, they will fade away, and with them, perhaps the final remnants of structure in the universe. This slow dissolution has implications not just for black holes, but for cosmology, quantum theory, and even the ultimate fate of the universe. It forces us to confront fundamental questions about entropy, time, and what it means for something to disappear. Stephen Hawking once joked that black holes aren't as black as they seem. They glow with a faint whisper of the universe's most mysterious truths. That whisper may be the echo of quantum mechanics itself, reaching out from the edge of reality to show us how much we still don't understand. Stephen Hawking gave the world a new way to see the universe, not as a static collection of matter and rules, but as a dynamic, mysterious place where even the most unyielding objects, like black holes, are subject to change, to time, and to quantum uncertainty. Hawking radiation stands as a bridge between the known and the unknown, a clue that the universe is more interconnected than we imagined. Gravity and quantum theory, so often in conflict, meet here at the edge of a black hole, where light escapes the darkness and time begins to unravel. One day, in the far future, the last black holes will wink out, leaving behind a silent, cold universe, but also the legacy of what they taught us. They will leave behind the echoes of a brilliant idea, a flash of insight that pierced the event horizon and brought us closer to the ultimate truths of nature.